All right. All right, welcome back, everyone. I'm Mike Zarin. I'm the vice president of basketball at the Celtics. And though I wasn't involved in picking the speakers for this section, I'm particularly excited about it because at the very first NESSIS, my hair's gotten whiter than Ben's has, so thank you for not using me. We were talking about using tracking data, and actually at the second NESSIS, Brian Kopp from Stats and I had a meeting outside that led to us being the first NBA team to install tracking cameras. And the operators of those cameras were actually HSAC students that were involved in getting NESSIS organized. So it's really cool for me now to be here and introduce a section of papers that are all about using that tracking data. Would have happened with, even if the Celtics hadn't been the first team, there would have been tracking data coming anyway, so I don't want to get too excited about that. But it's just fun for me to have seen the whole evolution of this and look back a little bit since this is the test NESSIS. So without further ado, here's some movement and shot dynamics papers. First, we have Judy Zhu. Judy is a graduate student in the MBA program at MIT, having earned her BA in math with a minor in data science from Rice in 2025. She's contributed to NCAA basketball scouting and collaborated with an NBA coach to develop innovative performance metrics. A passionate sports enthusiast, she aspires to pursue a career in the sports industry after graduation. So, Judy Zhu.
Hi everyone, my name is Judy. Thank you so much for being here today. And I'm here to present my research on the ball path curvature and in-game free throw shooting proficiency in the NBA. So imagine you're a basketball coach working with a player on the free throw line. You have watched thousands of shots, both in practice and in games, and you start to notice a pattern. Some players' shots just look smoother than others, but you just can't tell why. Coaches often repeat the saying that a smooth shot is a good shot. Yet when you actually try to explain what a smooth shot entails or to measure it, you quickly realize that it isn't that simple. Is smoothness about the arc of the ball, the rhythm of the motion, or the way that the ball leaves the shooter's hand? You can see it, you can feel it, but you just can't measure it. This is exactly the dilemma that the NBA shooting coach Dave Love faced. He wanted to help his players improve at the free throw line, but he lacked a concrete way to quantify something as elusive as smoothness. And too often, coaching advice in this area relies on a subjective observation, essentially meaning eyeballing the shot and trusting intuition. And then recognizing this limitation, Coach Love approached Dr. Scott Powers, my professor in statistics and sports analytics at Rice University, and me with a challenge. Could we actually develop a rigorous, data-driven method to measure smoothness and test whether it actually contributes to in-game performance? And that challenge became the starting point of this project. Before getting into our approach, let's take a step back and look into why this matters. So free throws are not just routine plays, they're actually pivotal. In fact, an NCAA study showed that about 20% of all points come from the free throw line, and that percentage actually increased in the last 5 minutes of games where the pressure is the highest. And because of this, free throw mechanics have been studied extensively. Researchers have examined factors such as release angle, ball speed, backspin, and even micro-timing of muscle activation in order to understand what separates a make from a miss. And these studies are valuable, but almost all of them are conducted in a controlled experimental setting rather than in real games, if not simulations of hundreds of thousands of shots. Now, one principle has consistently appeared in both coaching wisdom and academic literature, which is the idea that smoother shots are better. So it is believed that smooth and continuous shots tend to produce more consistent, repeatable mechanics in shooting. But here's the catch. Until very recently, nobody had a clear, quantitative way to measure smoothness. That changed in 2024. Slagers and Love introduced a framework that models the ball path during a shot using curvature-based metrics. And in their controlled experiments with professional players, they showed that better shooters tend to have a sharper transition from the backswing of the ball to the forward motion of the ball. And that higher terminal curvature, which essentially means roughness near the ball release phase, was associated with lower accuracy. And our study builds on this work, but with a twist. So instead of controlled experiments, we apply curvature-based metrics to in-game NBA data collected by the second spectrum technology. And by doing so, we aim not only to validate their findings on the real-world conditions, but also to provide a robust and repeatable, generalizable framework for evaluating shot smoothness and accuracy at the highest level of play. So now let's dive into the data we use for this study. Our data includes 515 in-game free throws taken from the 2023 to 24 NBA regular season, coming from 35 players averaging about 50 attempts per player. And we use optical tracking data from the NBA's second spectrum system, which records the ball's position in 3 dimensions, X, Y, and Z, at 25 frames per second. And this level of detail allowed us to reconstruct the full trajectory of each shot and analyze its motion dynamics. And in this study, we focus on the sagittal plane, which is given by the figure in the middle with the X and Z axis. And for performance outcomes, we pair this tracking data with each player's seasonal free throw percentage extracted from Basketball Reference, and that way we could link our curvature-based measures of smoothness directly to actual in-game shooting success. And now that we've set up the data set, the next step is to figure out how to actually measure smoothness. And to do this, we built on curvature-based modeling approach developed by Slagers and Love in 2024. But because we are working with noisy in-game tracking data, we, instead of clean lab-based recordings, we had to adapt and extend their methods. So in particular, first thing we would do is to standardize the ball trajectories across players so that every shot could be compared on the same footing. And secondly, we modeled these ball path trajectories mathematically to calculate curvature metrics, which capture how the ball path bends over time. And finally, we link those curvature metrics to each player's free throw percentage using statistical models. So the first step in our analysis was to define what part of the ball motion we want to study. Essentially, we need to agree on where the shot path begins and where it ends. So in earlier work, they defined the path using the shooter's elbow and hand position because they had limb tracking data. But in our data set, we only have the ball tracking data, so we have to adapt. We define the start of the ball path as the moment when the ball is farthest from the player's body, which corresponds to the first elbow in the S-shaped motion of free throw. And then we define the end of the path as just right after ball release, specifically 2 frames, which is about 0.08 seconds after the ball reaches its maximum speed. And that's a point where the ball is essentially out of the shooter's hand. And here the figure shows an example. So the green dot marks the start of the path, and the red dot marks the end. And by standardizing shots this way, we ensure that every trajectory we analyze start at the beginning of the backward swing motion and ended right around the release. And then we parameterize time for each shot so that the first observation occurs at time tau equals 0, and the last observation occurs at time tau equals 1. So we have a sequence of evenly spaced points in time. And then after standardizing the start and end of each shot, we needed a mathematical way to model trajectories so that we could compute smoothness. And for this, we used Bezier curves, which are parametric curves defined by a set of unique control points. And they are widely used in computer graphics because they are smooth, continuous, and differentiable. And those properties make them ideal for motion analysis. Furthermore, the coordinates of a Bezier curve are polynomial functions given by a set of control points weighted according to the coefficients of a Bursian polynomial. And formally, a Bezier curve of order n is defined this way, Bn of tau. And here we have n plus 1 control points, and 1 being the start point of observed data, and 1 being the end of the observed data. And each pi is a control point, and the coefficients are just the rest of it, the Bursian polynomials. Therefore, at tau equals 0, the curve starts at p0, and at tau equals 1, it ends at Pn. And in our case, we used an 8th order Bezier curve, meaning that we had 9 control points. Therefore, the question is, how do we choose the control points so that the curve best matches the actual observed trajectory? So we start tackling this problem by converting the Bezier expression to matrix form. So for each observation tau j, the Bezier curve, can be expressed in matrix form like this, where Tn is a row vector of powers of tau j, Mn is a lower triangular matrix of binomial coefficients, and Pn is just a matrix of control points. And then suppose we observe the ball at m+1 evenly spaced time along this path, we'll get this set y. And using the Bezier curve in matrix form, we get y hat, which are the fitted curve points. And so what we want to do here is to minimize the error between the fitted curve and the actual curve. And therefore, we solve a least square problem. And this problem has a closed form solution, and this is how we found the best control points that define the smooth Bezier curve that most closely approximates the observed trajectory. And here on the right, this is an illustration where the black dots are the raw ball tracking data, and the blue curve is the fitted Bezier curve, and the green dots are the unique set of control points. And you can see that the fitted curve follows the observed trajectory quite closely, capturing both the backswing and the forward motion. And then once we have fitted a curve, we can compute curvature, which is a great measure for smoothness. So for a two-dimensional Bezier curve, the curvature is defined as k of tau, like this. And then we take the first and second order derivative of the Bezier formulation and then plug them back into the k equation. We get a final expression here to calculate curvature at any given point on the curve. So just to summarize what we've done so far, first we fit Bezier curves to observe free throw trajectories using least squares, which gives us a smooth and differentiable representation of each shot. And then from these curves, we can compute curvature to quantify smoothness at every point in time. And once we had curvature defined, the next question was, how do we summarize it into a single measure of smoothness for each shot? So we hypothesized that smoothness matters most near the release of the ball, and early fluctuations in the shooting motion are less critical. What really counts is whether the path is stable and consistent right before the release. So to capture this, we introduced a weighted curvature integral, which aggregates curvature over the entire shot path, but emphasizes the latter stages of the motion. And formally, for a weighting parameter L, we define sigma L as this. Therefore, if L equals 0, this just reduced to the unweighted average curvature of the shot, but as L increases, the integral places progressively more weight towards the end of the shot, and converging to the terminal curvature as L approaches infinity. And here this figure illustrates the weighting process. The top row shows the weighted curvature profiles for L equals 0, 3, and 5. And the bottom row shows the corresponding cumulative integrals. And notice how as L increases, the latter part of the trajectory dominates the integral, meaning that the metric becomes more sensitive to the smoothness at the release point. And this allows us to test whether late-stage smoothness rather than just overall smoothness is a key factor in predicting free throw accuracy. So here I want to use a quick example to illustrate the curvature calculation and see how it corresponds to what we see in actual shots. So here's a sample shot from Steph Curry, and on the left is his real-life shot path, and on the right is the curvature and unweighted curvature integral plot. So as you can see from the top right, there is a peak midway through, in curvature midway through the shot, which corresponds to the second elbow of the S-curve between the backswing and the forward motion of the ball. And this elbow always has to have the max curvature along the entire ball path. And in Steph's case, the max curvature is right above 1 per foot. And on the bottom right, you can see there's also this gradual accumulation of curvature. And now let's compare this to a Giannis plot. So his trajectory shows a much sharper kink at the same stage. And this is captured on the curvature graph with this huge spike, nearly 25 per foot. And the cumulative integral also rises rather abruptly. And in other words, so Curry's motion is smooth and more evenly distributed, while Giannis' shot path contains some sharper, high curvature bend right before release. So this example illustrates how curvature metrics translate visual intuition into quantifiable numbers. So we computed the curvature metrics for all 35 players in our sample. On the top left, you see the distribution of maximum curvature, and in other plots, the distribution of our time-weighted curvature integral with L equals 0, 3, and 5. And notice that all the curvature metrics are kind of skewed to the right. So that means that most players cluster at moderate values, but a few players who have the highest late path curvature integral stand out with less smooth release mechanics. And on the other hand, free throw percentage looks fairly symmetric, ranging from 50% up to 93% with a standard deviation of 12%. For example, Rudy Gobert, PJ Washington in our sample are near the bottom of our distribution, around 65% free throw. And Steph Curry, Klay Thompson, and Damian Lillard anchor the top end of over 92% of free throw success. So while free throw performance is relatively balanced across players, we can see that smoothness metrics are heavily skewed, suggesting that a small number of players deviate strongly from the norm. And the purpose of developing curvature metrics was to see whether shot smoothness is actually linked to performance. And in our practice, our outcome variable is each player's season-long free throw percentage. We chose this because it reflects real-world performance under pressure and is widely accepted as a summary of free throw ability. It also has the advantage of being based on hundreds of attempts per player compared to around 15 shots for which we have detailed tracking data. And to link curvature to free throw success, we first averaged each player's curvature metrics, both maximum curvature and weighted curvature integrals across their tracked shots. Then we ran weighted least square regression, regressing season-long free throw percentage on those curvature metrics. And intuitively, this means that for players like Giannis, who took hundreds of free throws, contributes much more precise information than a player who only shot a few dozen of them. And finally, for each curvature metrics, we tested a null hypothesis against an alternative to determine whether smoothness is significantly associated with free throw percentage. And here are the weighted least square regression results. So for every single metric, maximum curvature, the unweighted integral, and weighted integrals, they are all statistically significant at a 1% level. And this means that smoother box shots are consistently associated with higher free throw accuracy. And the coefficients are all negative, which is what we accepted. Higher curvature, meaning that bending and roughness in the shot corresponds to a lower free throw accuracy. And importantly, the time-weighted integrals show the strongest predictive power with L equals 5. The model explains 33% of the variance in the free throw percentage across players, which is a remarkably high number for this kind of behavioral study. And this also highlights the finding that while coaches traditionally think that how a player brings up the ball is more important in determining free throw success, our study shows that the terminal release of the ball is more significant. And then here you can see the regression fits more directly. Each plot shows one curvature metric on the x-axis and free throw percentage on the y-axis. The blue points are the individual players, and the black line is the regression fit. And the shaded region is the 95% confidence band. And look at the bottom two plots where we use weighted curvature integrals. These bands are much tighter, meaning that there's greater precision, and this tells us the smoothness near the release is especially important. That means the less bendy and more controlled the ball path is right before release, the higher the player's free throw percentage tends to be. But interestingly, our study, one of the findings differ from Slager's and Love's earlier lab study, where they found that maximum curvature could be beneficial for shooting performance in jump shots. But in contrast, here we find that maximum curvature is actually harmful, where higher max curvature will lead to lower free throw percent. So why the difference? We think that it likely comes down to context. Their study analyzed the three-point jumper shots taken by lower-level professionals, namely the NBA G League, in practice. However, our study analyzed free throws by NBA players under real game conditions. And these contradictory results are especially interesting because from basketball domain knowledge, we would have expected lower max curvature to be more beneficial for three-point shots because one-motion shooters with lower max curvature allow them to generate greater power for shots from longer distance. However, explanation still remains an open question. Therefore, to summarize the results, all curvature metrics significantly predict free throw percentage. The strongest predictor is the weighted curvature interval with the highest L, which emphasizes smoothness right before release. And thirdly, this provides quantitative support for what coaches have long believed: smoother shots, especially at the release point, are better shots. And most importantly, these findings validate that we can take intuitive coaching idea that a smooth shot is a good shot, quantify it rigorously, and test it in real game data from the NBA. And before wrapping up, I want to acknowledge some key limitations of this study. First of all is the complexity of free throws. So free throw shooting is influenced by many factors beyond curvature. We have release angle, ball speed, muscle timing, and biomechanics. And our approach only captures one slice of that complexity. And secondly is that our analysis focuses on the sagittal plane. So this means that any lateral deviations, how the ball moves from the left to the right of the player's body, aren't accounted for. And thirdly is model sensitivity. So curvature-based metrics based on Bezier curves are very susceptible to parameters choices. For example, the number of control points or the exact start and end point of the shot. So reproducibility will require careful and consistent parameter selection. And then looking ahead, future work could build upon this foundation in several ways. One promising direction is to integrate biomechanical data, linking joint level motion with ball tracking to form a more comprehensive picture of how different part of body coordinate to influence the shot success. Another avenue is to segment the shooting motion into distinct phases, much like how we emphasize the latter part of the shot, so that we can isolate the backswing, the transition, the ball release, even the follow-through to determine which stage contributes most to the performance. And another further open question is the role of release speed, which remains ambiguous because faster releases may be helpful, may provide helpful advantages in game situations, but could also come at a cost with reduced smoothness and stability. So ultimately, advancing this research means moving forward with a more holistic framework that combines ball tracking data, biomechanics, and statistical performance to deepen our understanding of what makes a successful free throw. And that's all for my presentation. Thank you very much.
They don't tell you when you agree to moderate these sessions that you have to throw the cube. So we got some time. What's that? I'll try not to hit anyone. We got questions up here. I'm actually going to ask the first question. So Second Spectrum has to do some smoothing on the data first before it's like sent out or created to you. I don't know if you know that. So I was curious if you'd spoken with them because you're smoothing something that's also itself smoothed.
So like the data that's sampled at 25 frames per second are already smooth?
A little bit, yeah, because like any, the 6 cameras, there's occlusions, there's other things, and so the dots are actually not all exactly where they are in the final output data that you get. They do a little smoothing to begin with, so you might want to talk to them about that. Didn't know if you knew that.
I didn't
All right, I'm going to make my way up there. I know there's some questions up there.
Sorry. I was wondering, I think you might have mentioned it in the last slide a bit, but of course, if the ball contacts the rim, then spin rate's very important. So have you considered, I don't know if you have the data, but that might interact with trajectory parameters, like the backspin rate of the shot to predict free throw success?
Yeah, that's a very good question. I don't think we had data on the ball's backspin aspect, but I totally agree with you that the backspin would also influence the shot success as many other factors do. But
Thanks.
unfortunately, we didn't have the data.
I got told I can't use the box, which is much less fun. where was a question up here, no? Oh, all right, that's fine. I'll make my way up here. You're good.
Hi. Two questions, hopefully quick and related. The first one was, I was curious if you looked at all, like, because you're comparing across players now, the curvature. Have you looked at all, like, for the same player across different shots, if you look at the curvature and the smoothness, if you can predict, like, makes or misses with respect to their own sort of, like, regular trajectory? Does that make sense?
Yeah, that makes sense. So you're talking about within a player's 15 shots, like how stable are the shots?
Sure, yeah. I guess,
Yeah.
and I guess separate question, but what did you not have access to more than 15 shots? Because I guess with 15 shots it could be a little
Yeah, the data
hard.
was provided by the coach that we collaborated with, so we didn't get to like choose the players or the number of shots that we had. But like you raised a very interesting point. It actually covered in the study that we built upon. So in their study, they used the standard deviation of intra-player release velocity as a proxy for free throw success. So they're basically saying that like more stable shots, like if a player has the ability to like make consistent shots, then it's a better thing, like
Okay.
for the overall success.
Got it, okay. Because, sorry, my related question was just like, if you compare the limb size of these people, if like it changes the smoothness, like for example, if you're Giannis and you have long limbs, that it looks like a bigger dip when you bring it back because it's just the distance is larger. So I was just curious also if you looked at that at all.
Yeah, I think that's also a really good point. We wanted also to like incorporate players' heights and their like more of the players' data into this research too, because as you mentioned, like the different like heights of players or their like limbs, that would make a huge difference in how they would like bring up the ball as well as how they would shoot it. So yeah, those are very good points. I think in the future we'll definitely like incorporate that into our research. Thank you.
I'll make my way there. While I'm doing that, there's no spin data yet, but I think it might be coming soon. So nobody has it. It's not just you.
Hi, great talk. I'm curious about if you looked at all at like one motion shooters versus two motion shooters. Like in basketball, there's some players tend to shoot in like a smooth one motion shot, whereas some players prefer to kind of hitch at the top of their shot. I guess does your studies like kind of imply that a one motion like smooth shooting form is like an objectively better way to shoot?
Yes, but I think like what you're saying could be represented by like the max curvature that I talked about, because like whether that's a more distinct transition from backswing to forward motion or like lower maximum curvature would mean like a lower angle for that. I think that basically determines like a separates one motion shooter to the others. I think like back to the regression results, you can see like while max curvature has a negative coefficient, the absolute value is very low. So like more significantly, we think that the time-weighted curvature integral, which emphasizes the release ball release part of the shot, is more significant in determining free throw success.
Time for one more if there's any. Yeah, there's one down here.
Thank you. Hi, thank you. Great talk. I think my question is about, so you mentioned that there was another study which talked about three-point percentage and that the curvature wasn't as big as of an impact there because it was looking at like G leagues and the context was different. I'm curious if you think that, because I know when I was playing basketball, I was always coached to shoot free throws differently than I shot three-pointers because a lot of three-pointers are either like when you're already moving or off the dribble or something. Do you think that there's any chance that the fact that the shots are off the dribble or off a catch are different, causing the curvature to make less of an impact on a three-pointer rather than a free throw?
I think factors like that definitely will, but also like in their previous study where the three-point jump shots, they were in like a controlled environment and they were just like asking players to shoot from the three-point line, so there's no like dribble or catch and shoot involved anyway. So.
Got it. Thank you.
Yeah.
We could sneak one more in if there is one. All right, Judy, that's great. Thanks very much.
Thank you so much.